Thank you. I am Carlos Moro, an assistant professor at Texas State University. And before starting my presentation about assessing the impact of the nanoparticles, titanium dioxide nanoparticles on the environmental performance of mortars with recycled concrete aggregate, I want to acknowledge the co-authors of this presentation, that is Professor Belaili Zancos and Professor Francioso. So in this presentation, I'm going to first introduce the motivation of that. Then I'm going to explain how we proceed, like what procedure we follow, then show the results and also like the takeaways that we can bring home with this. So as in all this session, like in ACI, we are dealing with the CO2 emissions problem. These emissions are basically increasing like in the last 100 years with like being a very big, huge issue in the last 50. This increase in CO2 emissions are causing like, is the highest level that we have in 3-5 million years. That means like that we need to do something about it. This is causing a lot of issues like climate change, air pollution causing different premature deaths, also waste production that we are consuming and we are throwing like all these waste like on the sea or in landfills, and we have to do like a recycle procedure, and also natural depletion. So like we're getting new aggregate, for example, in case of concrete every single day. So we are basically at some point going to run out of these sources, and we also need to do something about this. Right now, we don't expect this to change because the population, it keeps increasing and increasing and increasing. That means that we will need to make even more impacts in the future, right? If we continue this line, because we will need to make more infrastructure, more buildings, more structures in general. So, for example, the United Nations have like 17 goals overall, and more than 40% of them are directly related to sustainability. That means that is a top priority right now. In terms of concrete, these are, and you all know that these are the main components of concrete, and cement is, and also you know that like is more, it emits more than 8% of the total CO2 emissions each year. But also the aggregates, the coarse and the fine, basically we are consuming them in more than 10 billion cubic yards every single year. That, as I mentioned, is a huge issue in terms of natural depletion, so we need to do something about that. But still, like concrete is a good product. It's like the material that we use to build like many different structures, like the Hoover Dam or the Guggenheim Museum. Indeed, it's the second most used material in the world. So since it's really highly consumed, we can do like a small impact will basically lead to a huge benefit in the environment. So in that case, I like calling that the sustainability in concrete materials is based on the rule of the 3 Ps. The first one is using the performance. That means if we increase the performance of our concrete, we can reduce the cement content needed to achieve that performance. So in that case, we will reduce the emissions. We also can reduce pollution directly with different beneficial effects during the service life, like promoting CO2 uptake or photocatalytic effect. And also, and not less important, is the production effect. What I mean is the production stage. That is basically reusing waste materials or byproducts. So in that case, we don't use new raw materials and deplete more the natural resources. But everything, in order to be sustainable, we need to account everything as a whole, right? Like using a holistic approach, so basically using a life cycle assessment account for all these different impacts during the service life. So in order to do that, we try to use recycled concrete aggregate, and we know, and it's known that this aggregate reduces the waste depletion, natural depletion, and also the waste generation, right? Because we are not throwing in landfills, but also it reduces the strength. Since it reduces the properties, it cannot be a sustainable option. So we were thinking that if we add nanotitanium dioxide, that is like a small material, we saw that this alone like increases the strength. So we were thinking, what happens if we use nanomaterials increasing like a small amount of this nanomaterials could overcome the decrease in compressive strength that the recycled concrete aggregate has. And for that, we did a life cycle assessment in counting for all the different impacts until the production stage, and also mentioning that we didn't use coarse aggregate, we use recycled fine aggregate on that. That normally is also a part of the recycled aggregate that is not considered either. So this the life cycle assessment basically is a technique that we use to assess the different environmental aspects and also the impact that it can have in the environment. Not only CO2 emissions, but also other things. So in that case, there are like different phases. Like the first one is the goal and scope. That is a very important phase because you need to set up and define your system boundary. That means until what point you are accounting all these impacts, and also the functional unit that you are going to use. Then, like the life cycle inventory that I'm going to mention as well, and the life cycle impact assessment, that is basically the categories that we are going to use. And then you interpret the results and you analyze all results, but in all these phases. So for this study, we used 12 different mixtures with 3% of recycled aggregate. That means natural aggregate 100%, 50-50, and then 100% recycled aggregate, and 4% of nanotitanium dioxide from 0 to 2%. We did the system boundary as a cradle-to-gate, but I'm going to mention later what happens later on. Okay, so like we also have like some hypotheses of what happened next. And as a functional unit, we're going to use 1 cubic meter of material with a given compressive strength. That means that we did compressive strength, and then we modify the cement content in order to equalize and achieve the same performance for all the mixes. Okay? For the life cycle inventory, we use different sources like the European platform, but also other previous research. And for the categories used, we use the Tracy analysis, well, Tracy and also the European one that is called CML. And not only we use the categories included in those, but also included waste generation and abiotic depletion, because whenever we are dealing with a recycled material, we need to use those in order to have a fair analysis. So our results show very similar, like regardless of the methodology used. That means that the American Tracy and the European CML show more or less the same results. But also it shows that, like, as expected, recycled concrete aggregate was very useful, like to help the waste generation and the abiotic depletion, and that the nanoparticles have a comparable performance compared to the reference sample with no nanoparticles, except for the energy consumption that is higher whenever you are producing these nanoparticles. If you focus only on global warming potential, so I show global warming potential or CO2 emissions like on the y-axis, and then different types of nanotitanium dioxide with recycled mortars. That means that this is 100% recycled concrete aggregate. We can see that a small percentage of nanotitanium dioxide help decrease because of the increase in compressive strength. So in that case, you can reduce cement content and you can reduce the emissions. But if we go further, that means that we use 2% of nanotitanium dioxide, then it's not useful anymore, because basically you need more cement to achieve the same properties. And again, like this is a recycled fine aggregate that usually is the part of the aggregate, the recycled aggregate that people don't like, because there are like more residual mortar stuck in it. In this case, we see the reduction of the CO2 emissions per cubic meter of mortar compared to the reference sample. That means that we have 3 groups, depending on the percentage of recycled aggregate that we have, and we are always comparing with the reference one with no nanoparticles. That means that the red column is basically 0% recycled aggregate, and we are comparing with 0% recycled aggregate. The green one, we are comparing with 100% recycled aggregate all the time. Okay? We can see that with a small percentage of nanotitanium dioxide, the CO2 emissions are improved. That means that we have lower with higher amounts of recycled concrete aggregate. That means that the recycled concrete aggregate is playing a role here. Why is that? because the recycled concrete aggregate has a higher porosity. That means that the nanoparticles can improve even further the densification of the microstructure. So in that case, it can improve even further the compressive strength and then reduce the cement content needed to achieve a similar performance. If we go further with higher percentage of nanoparticles, the results show similar effects that we saw before whenever we were comparing the global warming potential directly, that basically if we use higher amount, maybe it's not as useful or as beneficial anymore. And we have like higher emissions, for example, with the 2% compared to the reference samples. However, as I mentioned at the beginning, system boundary is a key thing here, and this is a cradle-to-gate. That means that we are basically producing the mortar and then we are stopping there. That means that we are not using any effects that this material has later on. So also we saw that like if we use the phenolphthalein test, basically in this case it measures the carbonation of that the samples could have. And I show like going down, that means that we use more recycled aggregate, and going to the right, that means that we use more nanotitanium dioxide. And we can see a trend here that if we use more recycled aggregate and more nanotitanium dioxide, the carbonation is faster and faster. That means that we are promoting CO2 capture during the service life. What does this mean compared to the left figure? That means that we still have a chance. Okay? We still have a chance that if we can uptake this percentage of CO2 during its service life more than the reference sample, our mortars are going to be even more sustainable, are going to decrease the overall impact that these materials has. And not only that, but like in the 0.5% of nanoparticles with 100% of recycled aggregate that we already had a negative value compared to the reference sample, we can improve even further. So having said that, like our conclusions were that the small percentage of nanotitanium dioxide, that means 0.5%, shows a reduction in the CO2 emissions, especially in mortars with recycled aggregates. That means 50 or even going further, 100%. That the results suggest that using recycled aggregate in combination with nanotitanium dioxide promote and accelerate the CO2 uptake. That means that we are uptaking faster, so we are not emitting that much to the atmosphere and the imbalance is lower. And also that if we consider the holistic approach and we consider all the beneficial effects that also these nanoparticles could have, like the photocatalytic effect, the combination of recycled concrete aggregate and nanotitanium dioxide may decrease the total environmental impact during the service life, well, during the whole service life. And these are the references that I use, and then like if you have any questions, I will be very happy to answer them. Thank you.